All right, well, if you're just joining, if you weren't on the previous sessions, welcome and thanks for joining the EMC workshop this week. My name is Todd Toporski. I'm just going to quickly go through this intro so most people don't have to listen to the same thing twice, but I have over 25 years of designing and supporting EMC compliant systems and board designs. I'm a principal FAE at MPS, and I've been here for a little bit over 2 years, and I'm supporting primarily automotive customers. Before that, I was an FAE at TI for a little bit over 16 years, also supporting automotive. In the first 11 or 12 years of my career, I was a hardware and system designer, designing a variety of products. In each of those different kinds of markets, I was very involved in hardware and software design, as well as the PCB design and meeting compliance requirements. So for this topic today, we will start off with trying to understand DC to DC converter waveforms. And then we'll jump into our approach for or review an approach for debugging radiated EMI from a DC to DC converter. And then finally, we'll look at some circuit modifications that can be used to achieve passing results. First off, let's take a look at some DC to DC converter waveforms. For our investigation today, we'll be using the MPQ 9842, which is an automotive buck converter that has integrated high side and low side FETs. It's powered from 12 volts or car battery, and then we'll be bucking down to 5 volts at 2 amps. When we look at any type of buck converter or DC to DC converter, we need to be cognizant of the different waveforms that are being produced by this circuit. Some of them they're all time varying, obviously, because it's a switching regulator, but there are some critical waveforms that may be occurring at the input side, others that are occurring at the output side. And it just helps our understanding for debugging EMI if we can relate to what these waveforms are. So here on the input side of a buck converter, we typically see very sharp current transitions. This current is being pulled out of the capacitors to provide energy to these to the FETs that are switching here, which are trying to pull current from the input and energize this inductor at the output side. So each time these switches are turning on and off, they are creating these very high DIDT type waveforms, which can actually be measured here at our input capacitors. And the ones that will react the fastest to these quick transitions are usually the ceramic caps, just because they're very low ESL, they have very low inductance, and they're the ones who will provide this initial very fast response for the current. If we were to look under the hood at this buck converter and see the high side and low side FETs that reside inside of this device, and we could measure the current there, we would see that the high side, when it turns on, has a waveform that looks like this. Very sharp current transition. Then it ramps up at a rate related to the inductor value here. And then when it turns off, it drops back down to 0. And the low side, on the other hand, turns on when the duty cycle is in its off cycle. So this will be the slope of the ramp that decreases related to the inductor current. And then it goes to 0. Then when the high side turns on, this is at 0. Low side turns on, this goes back on, and it continues. Most of us have, who've been working with power electronics and DC to DC converters have probably measured a switch node once or more. This is the very common waveform we see. It looks like a square wave or a rectangular wave where the buck converter is switching off of the 12-volt supply, and it transitions between close to 0 volts up to VN. And the duty cycle of this waveform and how long it turns on and how long it turns off will ultimately determine what our V out is that we're trying to regulate here. But the important point here is that these are very high dVdt edges, which can be measured at the point where the two FETs are tied together along this switch node trace and out to the input of our inductor. And then if we measure the currents in the inductor or between or at the output of the inductor, we'll see that it has this characteristic. This is our typical ripple current that is that has a fundamental frequency that is what that is determined by the switching frequency. So in this case, it would be 2.2 megahertz. And you know what we see here with these large peaks is not super high DIDT, but there's still a lot of energy in this waveform because it's a lot of current being switched and it's going through a magnetic component. So it's definitely providing a strong magnetic field, even at the lower frequency, or particularly at the lower frequencies where it's switching. And then if we were to look at the return current coming back from the load, from our output caps and then back to the low side of the power FET, what we'd see is a current that looks very similar to the inductor current, only it would be on the ground return. So we can take that and apply it to our circuit here and trying to understand what we're viewing with our printed circuit board. So this is the MPQ or EVQ 9842 eval board. We can locate the input caps here as shown, circled, and these we know will be our high DIDT caps. And we should expect that we're going to be able to measure a very strong H field off of these. You know, if we have near field probes and we probe around the board, this is one of the areas where we'll pick up strong H fields. If we were to also measure around the IC or just above the IC, we can pick up both strong E and H fields because we have high DIDT currents circulating in this circuit when the FETs are turning off and on, as well as high dVdt because we're switching from our input of 12 volts down to a lower voltage. At the switch node, we have high dVdt, so we're always concerned with strong E fields coming off of this node. That's why we try to keep it as small and short as possible. And then of course our inductor, which is a very strong magnetic field, always coming off of this part, but we have to be aware that there are also strong E fields, strong parasitic E fields that can be generated from these parts as well. So now we get into an actual example using the 9842, where we do some measurements and then try to do something useful with them. So first of all, before performing measurements, we want to carefully look at the schematic for our test board. In this case, this device comes with an EMI filter populated, so it has a 4th order EMI filter on the front end, but for this test, I removed these. I basically shorted out the 2 inductors, L1 and L2. I made sure it was configured for 5 volts on the output, made sure the frequency here was set to 2.2 megahertz. And I also wanted to run this test without any spread spectrum to see how well it would perform. So this board actually has an optional spread spectrum circuit footprint on it, which can be populated, but I made sure that that was removed so that it had no impact on my testing. So starting off, I set this up in our EMC lab here in Livonia, and I used a standard 2-meter harness, connected it to the car battery and Lizen, and I used some power resistors for my load, which would allow me to deliver 2 amps from my 5-volt output. And then I ran my first scan, and for Monopole, what I got was this result, which is obviously quite a few spikes here in this range between 2 megahertz and 30 megahertz. Note that all these are passing because there are no limit lines in this region or this region. However, at 6 megahertz, there's a specific limit line that we need to meet, which in this case, it looks like we're failing by a small margin. It looks like we're about 0.82 dB over. So it's marginal, but at any customer, this would be considered a failure. So, here's one issue that we've found so far that we're going to have to deal with. Next, I ran some measurements for Bicon and log. So I covered my range from 30 megahertz up to 1 gigahertz. And I got these measurements. At first glance, these look, like there's a lot of noise, but low level noise here at about 0 dB or less. From 30 megahertz up to about 300 megahertz. But then once I get to 300 megahertz, I'm getting pretty close to a limit line here. So what I did digging into this is I found that we are actually failing by just under 2 dB at 301 megahertz, which is considered the RKE band, or remote keyless entry band in automotive. And you can see here when you zoom into it, we're just a hair over on the green waveform, which is average. So our peak, which is blue, is well below the limit line, but the average, which is green, is just creeping above it a little bit. And then there's also a couple other peaks here that are just below it. So, prior to doing these measurements, I did a preliminary board layout review. I looked at the PCB layout. It looks pretty good. I was expecting to get pretty decent results. And I wasn't expecting there to be any major problems. So now that I've done these measurements, in Monopole, I've got one frequency, which is borderline at 6 megahertz. The Bicon range is all passing and looks pretty good. Even though we do have some noticeable noise spectrum, it's well below the limits. And then once we get up into this higher frequency range, we have one failure at about a 301 megahertz in the vertical polarization, and it's just under 2 dB. So overall, not bad, but we definitely need a few improvements to try to fix these issues that we observed. So our goal is to try to pass at these 2 problem frequencies with not by a little bit, like not by a dB or 2, but hopefully with as much margin as possible. So first, before we start making any changes to the board, I want to take a step back and just kind of think about this related to the near field and far field and some of the information we reviewed in the previous session, if you were part of that. And so, for each one of these problem frequencies or frequency range that's a problem, we can go in and determine the wavelength based on that frequency using the standard formula that we've learned, lambda equal to C over F. And then we can define a near field boundary as lambda over 6 distance from our noise source. So for Monopole, plugging into this calculation here, I come up with a wavelength of 50 meters, near field boundary that's just a little over 8 meters. Since we know our antenna is 1 meter from the cabling, our device under test is about 1.5 meters. We know that this problem is near field. Therefore, we can make a pretty good assumption that we're measuring E fields, strong E fields that are coming either from the DUT or the cabling, or perhaps both. Excuse me. With Bicon, we're passing, so there's nothing I calculate there. And then for log, we can run the same calculations and determine that our near field is at about 17 centimeters from the board. So the measurement that we're making is definitely far field in this case. You know, we're measuring an electric field with our antenna setup, but you know, it's a component of the overall electromagnetic wave being propagated. So we don't know at this point, could this be an electric field or magnetic field on the board actually causing this wave propagation? Some other things to consider, you know, at 300 megahertz, it's kind of that range where it could maybe be the cabling, it could maybe be the circuit board. It's kind of that gray area. There could be a little bit of contribution from the cables, but I would guess, just based on some of my own experiences, that the board is probably more likely to be the dominant radiator at this frequency. So we're going to take a closer look and see if that's true. So our next step is we want to determine what our dominant noise source is. Is it our DUT or is it the cable? So again, at 6 megahertz, we think it could be coupling potentially from either the cable or the DUT, or maybe both. And at the higher frequency, we're pretty we're pretty sure that it's probably related to the DUT, but we'll take a closer look at that too. So how can we prove this, or what steps can we take for this initial assessment? Well, the first thing is to look at each one of these things separately. The circuit board or the DUT, for example, we can kind of determine its effects very easily if we have a metal enclosure or any kind of shielded box like this one. This is one that you can easily get on DigiKey or Mauser. You know, put your printed circuit board in there, or your product, whatever product you may have, put it in there. You can then take some aluminum or copper foil to try to shield the opening as much as possible, and then run a test and see what it tells you. For the cabling can be a little trickier. But if you think about it, there's a couple of things that you can do that could show some behavior differences. The first one, which I showed in my previous presentation, is wrapping some sort of foil or some kind of like a copper mesh or aluminum mesh around the cabling. I suggest that you insulate the cabling with either cardboard or wood on top and bottom before you wrap it. If you have a nick in the wire and you wrap it like this, you could short out your battery or cause your board to fail. And we definitely want to avoid these situations. So be careful, you know, try to put some insulation around your wiring. Then you can wrap foil and then try to tape it to the copper table so it has a very good ground connection. The other option, which you may not consider, but it makes total sense when you think about it, is to just simply take your cabling and make it very short. If we suspect cabling is the problem, if we take a 2-meter cable and then shorten it down to something that's 10 or 15 centimeters, for example, like these wires, which are used for conducted emissions testing, we can also make some observations and and determine just how much of a factor that cabling may be. One quick note here, I know in these pictures I'm showing cables that have little alligator clips, which we use here for quick comparison and quick A/B test comparisons. But when you're doing a real EMC test on a customer setup, we do not recommend using these clips. We recommend using very good connections, such as screw terminals, or soldering the wire directly to the board. You want to make sure you always have a good connection before you get too far into your debugging. Okay, so we start off in the monopole range, and the upper left corner here is our original measurement. And if we look at the two plots on the left side bottom is the same setup as the top, and with the DUT. Basically, the DUT is unshielded here, and it's also unshielded here. The only difference is the cabling. So I took my 2-meter cabling, I reduced it to 15 centimeters, and this is basically what I got. It's a little bit of an improvement, a reduction of about 3 to 6 dB at most frequencies. From this, I would say, yeah, there's a little bit of contribution from the cabling, but it doesn't seem to be very much the dominant factor. So then if I take my 15 centimeter cabling, replace it with 2 meters, and then I take my DUT and shield it, I end up getting something that looks like this. And this is a vast improvement, 10 to 15 dB, which leads me to believe that this is very much my dominant noise source. It's coming from our eval board, from the DUT. Then when I move to the higher frequencies and I do my measurements with Bicon and log, I perform similar experiments. I start off with my 2-meter cables to make my initial measurement. Then I reduce it to a much shorter cable. And what you see here is something that doesn't look very different. It looks nearly identical. You can see that some of the noise shifts around a little bit in some of these frequency ranges due to the different cable length, but the level of the noise isn't really getting higher or lower. So it doesn't really change much. I don't have plots for the shielded DUT for this case, but I did run the same experiment like I did in Monopole, but for this antenna, these antenna ranges. And I got something very similar, which was that all this noise in this area from about 400 megahertz down to 30 megahertz was significantly attenuated once I put it inside of a shielded enclosure. So again, from the cabling, my assessment was dominant noise is not coming from the cable. When I did the shielded DUT enclosure at the higher frequencies, I see that the dominant noise is coming from the DUT. And the same thing for the horizontal measurement. So I did the same thing for horizontal and vertical, and I get pretty much the same type of scenario. So to summarize what we have seen with our experiments in trying to determine our dominant noise source, for the near field measurements or monopole measurements, we determined that our DUT is very much the culprit, in that it's most likely coupling some electric field directly to the antenna. And then when we got to the higher frequency antennas, we could also see a similar, similar theme. Basically, the far field noise being measured around 300 megahertz and 400 megahertz, 200 megahertz. It was basically coming mostly from the DUT. So from that, we can determine, since it's far field being measured here on the antenna, for the higher frequencies, that we likely have either an E field or H field issue that we need to identify and fix. So for this case, and I alluded to this earlier, but in this case, filtering the cabling here coming onto the board could yield some small improvements like we saw when we shielded the cabling, but it's most likely not going to help us a whole lot. If we do pass, it'll be with probably a small margin. If we really want to tackle this problem and try to have the most significant noise reduction, we really want to take a closer look at our device under test and try to fix those issues locally. So now let's get into our next point in our analysis. So now we're going to investigate possible noise sources on the DUT. And we'll start off with one of the things that we touched on at the beginning, which is our input decoupling loop. First, we want to locate these caps on the board, and I want to try to shield these And the reason that I want to take this approach is because I'm just at this point trying to figure out if I shield anything on the board in any particular area, is it going to show a significant difference? You know, my end goal may not be to shield these, but right now I'm just in the process of trying to identify the root cause and see if I can make it change based on me tweaking a few things. So here, I can cover my caps with Kapton tape, which is just like a thermal insulating tape. I scrape off solder mask above and below these set of caps in a ground pour area on the top side of the board. Next, I stick a piece of copper tape over these caps, and then I add some solder to the tape and to the ground where I've scraped the solder mask off, so I have a good ground connection on the top and bottom. And when I do this change, I see what actually is not a whole lot of improvement. So here are the vertical and horizontal measurements, but just so that everybody can remember, you know, here on the left side of the vertical measurements, and the top is no modifications, and then the bottom is the modification with shielding the input decoupling caps. And if we look very closely here, there's just not a whole lot of difference between these two plots. And when I look at the horizontal side, the horizontal polarization with no mods is on top. Below it is this modification with shielding the input caps. It's not really a whole lot of difference here either. So overall, no significant improvements were found. So next, I want to go on and try a different component in my layout and in my design. So next, I'm going to go for the inductor. And so I'm going to follow the same process that I did for the input decoupling caps. I'm going to, you know, try to find some local ground near this place, scrape off the solder mask, cover it with some kind of an insulating tape or insulating material, put copper tape over it to act as a semi-shield, and then solder that tape to ground. When I do that, I actually notice right away that I have some improvements here. And it's more obvious on this slide. So when I compare my original scan of no modifications with this modification, which has only the inductor being shielded, I noticed right away that there's several dB of improvement down here below 150 megahertz. So if you look closely, the peaks here are a little bit higher in this range from 150 megahertz on down. On the bottom, you can see that they go down at least a few dB, several dB. And if I also look in this range from 300 to 330 megahertz, my average, which is my green waveform, actually drops a few dB as well. So that's good. On the horizontal polarization, I see something very similar, but I actually notice that there's a more dramatic effect up around 300 megahertz. I've got both my peak and average noise in this range, both dropping significantly. So even though our failure was here in vertical, I have noticed improvement in vertical, and I've noticed a big improvement in horizontal. So obviously our inductor is having something to do with that. Oh, I apologize. Somehow I jumped out of my slides. Let's start up again here. Okay, here we go. Sorry about that. So next, you know, I still have a sneaking suspicion that I may be missing something here related to the input decoupling. You know, just, you know, I've looked at a lot of converter designs, and you know, it's something just didn't sit right with me here, that when I shielded this, I didn't really see much of any difference. So I decided to go back and take a closer look. And, I looked at this, I pulled out the board layout, the all team files we have for the PCB layout. I took another look at the schematic. And so one thing I noticed is that the 9842 is not a symmetric VN device. So many of our new converters have symmetric VN pins where you have a VN and ground pin on opposite sides of the part, which allows you to put decoupling caps on opposite sides. So that this part is not that. It's a little bit older part. So even though it's not symmetric, it does have these caps positioned in a symmetric fashion. So they are connected to VN and to ground symmetrically, at least on the surface. But as I dug into this a little bit closer, I noticed that the ground return area for the top set of caps here was actually a little bit longer. And it had a longer path back to the power ground on the IC compared to these two bottom caps. So in essence, we were trying to form symmetric decoupling here, but with one of the return loops being slightly bigger on top compared to the lower one, I suspected this might be an issue. So I decided to go forward with trying a couple experiments here. At first, I removed both of these caps. I ran some scans. I didn't see much of an improvement. In fact, I think it got worse in a couple of areas. And then I went back and I just decided to add the small decoupling cap and see if adding that back, but then leaving the larger cap off made any difference. And when I did that, I actually saw some improvement. And so that's what these plots show for modification 3. Modification 3 is basically removing this C1A decoupling cap here on the left, the top left. And I noticed that it gave me some additional improvement in this case. And in this test, I had both the inductor shielded and this cap removed. So when I did that, comparing the vertical plots here, I can see I had basically additional reduction all across these frequencies here up to 300 megahertz. And I had some additional reduction here in this 300 megahertz range. So that was in the vertical polarization. When I look at the horizontal polarization, I did not notice as much improvement. So this removal of one of the input decoupling caps appeared to help me mostly in the vertical polarization. And, that's another data point for us to consider. So then the last modification I made was to take a look at the impact of the IC and how much noise this IC was actually contributing to the overall noise performance. So in order to do this, I did a similar thing. I kept the inductor shielded and I put a sill pad over the IC along with some other insulation. And then I taped over this entire region for the IC, switch node, and the inductor. When I did that, these are the results I got, which ended up being kind of mixed. I did notice some improvement in horizontal, but not so much in the vertical, which we'll take a close look at here. So when we compare the two vertical from mod 3 to this new mod 4 set of changes, it's very similar. Like you can notice maybe a couple minor changes, but nothing much. When I look at horizontal, however, I see that my noise actually looks like it's peaking up a little bit around 150 megahertz and below. So that's actually kind of degraded a little bit. But then up around 300 megahertz, it's really come down quite a bit compared to what it was here. It's come down by several dB. So there's another data point for us to consider as we move forward. So To summarize these modifications that we made and what we've been able to see in terms of improvement or no improvement, in modification 1, we shielded the input decoupling caps. We noticed no significant change. When we tried the second modification, which was putting a shielded tape over the output inductor, we had very noticeable improvement for both vertical and horizontal polarization. For mod 3, we kept the output inductor shielded still, and then we decided to remove C1A input cap, and we saw improvement for vertical polarization. And then for the last mod, we ended up getting some mixed results, and it's almost the kind of thing that we probably don't want to pursue, just because we may help in one area but hurt in another. So moving forward, this is probably a change that I would not want to consider seriously. One other quick note here is, for all these measurements, all these modifications were measured only at the high frequencies for Bicon and log. And at this point yet, we still don't know what the impact is on monopole. So instead of going back and doing my monopole measurements, I decided to move forward with just trying to make a couple changes per what we learned, and then try to do a quick retest on this board. So from what we just reviewed, these were the two biggest impacts: shielding the output inductor L3 and removing C1A. In a customer's application, as well as on our own eval boards, we try to avoid shielding as much as possible. We don't want the extra cost. We try to make it passing with just the components on the board. So for that reason, I decided to not shield the inductor, but to just try to find a different inductor, hopefully one that's a little bit smaller, has a little bit better EMI performance. And that's what I did. Here's a picture showing the input cap removed, and then the output inductor, which was originally this part number, which was a 4.7 microhenry 6 amp rated part, 7 millimeters by 6.6 millimeters by 3 millimeters high, kind of large, probably a little bit overkill for this circuit. So we could bump it down to something a little bit smaller, like this 4.7 microhenry inductor, which is closer to 4x4 in its area and only about 2 millimeters high. When I did this, I also had to go back to the standard CISPR setup and use 2-meter cables. So I made the changes to the board, added the 2-meter cables back in, and then I retested it. And so the top is the original scan. The bottom is with the updated board. And what we notice here is, for the average noise here in the green, we actually improved it by about 10 dB. I measured it specifically at 301 megahertz, which is where we failed before, and it's at 10 dB. And then in this whole range, it's approximately 10 dB better. And also in this range just below 300 megahertz, from like 270 to 300 megahertz, there's also some improvement of about 5 to 6 dB if you compare these waveforms with what we're seeing up here. One observation here is that the noise below 200 megahertz didn't look like it was much improved, but it was very similar to the original. So the presence of this noise could be due to adding back the 2-meter cable, or it could also just be due to not having a shield over the inductor. The inductor may give us the benefits in this frequency range, perhaps not so much in this range. The same thing with horizontal, ran the same measurements, adding back my 2-meter cables. And again, in this 300 megahertz range, I observed an improvement, actually not only in average, but in peak. The peak and average both dropped considerably here. But one trade-off that we see here is that the noise here, just above 400 megahertz, looks like it went up a little bit. Fortunately, it's still passing, and it's, there's still a little bit of margin there, but it's something that we should note is that fixing it in this range actually made it a little bit worse in this range. And then again, below 200 megahertz, we see about the same level of noise. And then for our last test, I went back and retested Monopole to see what the impact would be, going back with 2-meter cables. And here we ended up having a significant impact as well. We can see here the 2 megahertz was reduced by about 8 dB. In the range of 4 to 8 megahertz, all of these peaks were reduced by about 10 dB. In fact, our 6 megahertz is now passing by a good margin. And then above 10 megahertz, there was a little bit less attenuation, but still 5 to 7 dB of improvement. So the summary of these results was that we achieved our goal, using the methodologies that we stepped through and the experiments we tried. We reached our goal of making 8 megahertz pass. We're now passing by 10 dB. At 301 megahertz, we're now passing by approximately 10 dB as well. And we were also able to improve a few other frequency ranges. And one thing to make note of here is that we were able to do this by only modifying one component, which was the output inductor, and then simply removing another component, which was an input decoupling cap. So in conclusion, in this session, we discussed voltage and current waveforms and their associated E and H fields for DC to DC converters. We reviewed how to determine if our measured noise is actually in the near or far field. We looked at some strategies to determine if the DUT or cable is the dominant noise source that is measured by the antenna. We looked at strategies for debugging possible noise sources on the DUT. And we went through a couple DC to DC circuit modifications that led us to passing radiated emissions. So thank you for your time, and we can open it up to questions.
Great, thanks, Todd. Again, we're getting a little bit time constrained here. We have one fairly complex question, so let's take that one. The other questions, these are recorded by the system. I will add them to an email and send out answers to everyone there. But this one more complex one was, when adding the copper tape shields to cover various areas on your DC-DC converter circuit, the shield will also add parasitic C to the ground that will be determined by the insulator you add, for example, Captain, Silpad, etc., and its thickness. I'm not being critical of this method, just wondering if you've ever tried different spacings away from the component of interest, and if so, did it tend to make a significant difference? I get that the overall idea is to perturb and observe in order to figure out what parts are worth investigating, but I also wonder if the method could introduce spurious results that you could end up chasing. And let's keep it a pretty quick response to this one.
Well, that's yeah, it's a very detailed question, and that will be hard to answer in a very short response. But yeah, in general, I use this method more as a way, I think in the latter part of the question I said to perturb and observe, which is exactly what I'm trying to do. I'm trying to get a feel for what is the circuit, what part of the circuit is actually related to noise I'm measuring in a particular frequency spectrum. And so I know when I'm doing this, I could be introducing other parasitics. There could be other parasitic capacitance I'm creating. I could be altering the magnetic or the electric field coming off the parts such that it's maybe propagating in a different direction. There's certainly all these things that could be happening. But when I do this, I'm more trying to make a high level observation of what is changing due to a slight change in a component, whether I'm shielding it or whether I'm changing the value of a component. That's basically all I'm trying to do here. I'm not trying to read too much into it. If I was actually trying to create a shield to shield it, then I'd be more concerned with the height above the device and the distance that I need to minimize parasitic capacitance and things like that. But in this case, I'm not really concerned with that, because I'm just trying to use this semi-shield technique to figure out where my problems are. And then hopefully after I figured out where they are, I'm able to fix them using a method that doesn't involve a shield, most of the time. So if there's more to that question, I can try to answer it later in an email or response to the customer.
Great, thank you. And so yes, if you have a follow-up on that, and we do have a couple other questions, I will take those. Everyone that attended this session will just email those questions and answers back out to you probably early next week. So with that, I'm gonna thank Todd, and let's start to hand off to Mark for our final session.
Okay, thanks, Kelly.